On section 10.3, we're going to focus our attention on finding the error that is made when we use a certain number of terms of a Taylor polynomial. If we've got some function, let's say sine of x, that goes like this, and we come up with a polynomial that approximates sine for a while anyway. We use a finite number of terms, kind of follows nicely for a while, and then it doesn't follow. And the center of this would have been right here. What we're interested in saying, you know, from this x value right here to this x value right here, what's the biggest error? How far off could we possibly be using our approximation as opposed to the actual function? And I think we're going to see, and it's pretty easy to understand, that at the center of this interval, we're going to be locked on, and that the biggest errors are going to occur at the ends of these intervals. And we want to be able to figure out, we want to have a tool to figure out how big is the error. And so, in this example here, it says find a Taylor polynomial that would serve as a substitute for sine x on this interval with an error that is less than 0.0001. Well, I'm not going to do it graphically. What I'm going to do is this. I'm going to take the sine of x on my calculator. And prior to that, I'm going to show you the method here. I know that the biggest error is going to occur at one of these endpoints of the interval. I'll choose this endpoint right here. So the first thing I'm going to do on my calculator is I'm going to say, let's take pi and let's store it. And the store button is kind of just to the left of the 1 and the 4. Let's store pi in x. And then I press enter. And now the x memory location on the calculator contains the variable, contains the value of pi. So then I'm going to say sine x minus. And I'm going to put in my Taylor polynomial for sine. And Taylor polynomial for sine is x minus x cubed over 3 factorial. And if I stop there to see what's the difference between the actual and the approximation, I'm wondering, do I get a value where the absolute value of that difference is less than 0.0001? And the answer is no. So now I'm going to say, well, let's include the next term. I stop there and I compute that, calculate that. And is the difference less than this? And the answer is no. And I keep going. And I check this. And I see, is that difference? Now, if I had stopped here, I got a difference of 0.0069. That would have been the absolute value of the difference between sine and polynomial approximation. If I had gone to this term, 0.00045-ish, almost there, but not quite. When I include this term, For the first time, I get a difference. I get a value here of point, and I think there are 4 zeros. And so by trial and error and lots of trials, I have found the Taylor polynomial, finite number of terms, for the Taylor polynomial for sine, that will get me really, 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 really close as long as I stay within this interval right here. All right. Now, Taylor's remainder theorem, or Lagrange, it's usually on the AP exam referred to as Lagrange. This is the slight difference between the finite number of terms of a Taylor polynomial, like we just saw, that estimates the value of a function. And this looks kind of complex. Take some practice. The remainder after n terms. Okay, we just did remainder after how many terms? Whoopsie. 1, 2, 3, 4, 5, 6, 7 terms. The remainder after a certain number of terms is equal to, now, this guy right here. Now, this notation means we're taking the next derivative. So if we're looking for the remainder after 3 terms, if n is 3, then n plus 1 is going to be 4. We're looking for that next derivative. And what we want to do is, on our interval, we want to maximize the value of that next derivative. Maximum value of the next derivative. A is where we're centered. X is one of the endpoints of the interval. In the last one, we used pi. Okay, that's going to give us a maximum value for x minus a. Remember, a means the center of the interval, and x is one of the endpoints of the interval. And up here we used n plus 1 over n plus 1 factorial. Okay, so a different notation says let's maximize the value of that first, what we'll call it is the first unused derivative. Maximum value of the first unused derivative. X minus a to the n plus 1 over n plus 1. And that is going to give us the difference. And this is what we are going to use if we have a non-alternating series. If we have a series that does not alternate, and sine does alternate in our last example. If we have a non-alternating series, then this is our theorem that we're going to use. Okay. So, let's see what that looks like. We're going to see what that looks like actually in example 2. We're going to show, if we want to show that a Maclaurin series, something centered at 0, converges for all values of x. All we need to show is that each derivative has an upper bound. Okay, there's a maximum value of that first derivative. Now, let's take a look at this. This is the series for sine x. And I would like to show that this series converges for all values of x. Okay, it doesn't just converge from -1 to 1, it converges for all values of x. Now, if we think about f of x is equal to the sine of x, let's talk about its derivatives. Derivatives are cosine of x, negative sine of x, negative cosine of x, and then we're back to sine of x. And these just keep repeating and repeating and repeating. Do these derivatives have an upper bound? Do these derivatives have a value that they never ever exceed? And yeah, sine, cosine, negative cosine has an upper bound. It has a value that it does not exceed. It has an upper bound of 1. Therefore, this series converges. This polynomial series converges. For all values of x. Okay. Now let's go back to Lagrange. We're going to say that natural log of 1 plus x is equal to x minus x squared over 2. And it's pretty accurate, as long as x is pretty darn small. What we'd like to do is we'd like to estimate what is the Lagrange error with this approximation when the value of x, and I'll write this differently. I'll say the value of x is between negative 0.1 and 1. Well, now let's see. The remainder would be equal to the absolute value. Remainders are always positive. F n plus 1. C is the maximum value of a derivative. X minus a to the n plus 1 over n plus 1 factorial. Now, what was n? In this term right here, what derivatives were used to write these terms of the polynomial function? Well, I must have used the first derivative because I've got the x term. Remember how we write these. We've got f of 0, f primed of 0 times x, f double primed of 0, x squared over 2 factorial. So it looks like we must have used the first derivative to write this term. We must have used the second derivative to write this term. And so it looks like we're talking about the remainder after we have used two derivatives. So that means n plus 1 is 3. All right, so what is the third derivative? Let's see, we've got natural log of 1 plus x. And the first derivative is going to be 1 over 1 plus x. The second derivative, if I find the derivative of that, is going to be negative 1 over 1 plus x being squared. And the third derivative is going to be 2 over 1 plus x being cubed. So I want the maximum value of this third derivative using these values of x. Well, what value of x in this interval is going to maximize the value of this third derivative? If I want a fraction to have the biggest possible value, I need the denominator to be as small as possible. Therefore, I think I'm going to maximize the value of that derivative by using this. So I'm now going to write this guy. And I'm going to say that the remainder, after we've used the second derivative, is going to be equal to the absolute value of 2 over 1 plus negative 0.1 to the third power times, I'll use that same exponent, or I'm sorry, same endpoint of the interval, minus a, which is the center of the interval. Sorry about that. The center of the interval is 0. I've got to take that to the third power. And I've got to divide by n plus 1, which in this case is 3. And I've got to take the absolute value of this. So I put down my pencil, I pick up my calculator, and I figure out what that is. You should figure out what that is. If you need to press pause, do it. Come back and check and see. That's what I got as the error. Maximum value of the first unused derivative. One of the endpoints minus the center. Know how many derivatives you did use so that you know what n plus 1 has to be. I'm going to take some practice. This thing right here, we're not doing this one. That's actually one of the homework questions. Okay, next we've got alternating series error. Alternating series remainder is another term that's used. In an alternating series, a finite number of terms gives an estimate for the value of the infinite series. And again, the difference between the estimate and the value of the infinite series is known as the remainder. Okay. This is the key right here. The remainder, or the error, of the estimate using n terms is the n plus first term. In an alternating series, the error equals the first unused term. Okay. So, what is the maximum error of the alternating series used to estimate the value of 1 over 1 plus x? Now that's geometric, right? And it's geometric, and r is negative x, and so we know that 1 over 1 plus x, we've done this geometric series, 1 minus x plus x squared minus x to the third plus x to the fourth, and on and on and on and on and on. Well, we have used this as our estimate. That is our Taylor polynomial that we have used. What is the error? What's the difference between this guy and this guy when we get as far away from the center as x is 0.1? Well, if I look at the terms that I did use, those are these, this is the first unused term in the infinite series. That's the first one I didn't use when I cut this thing off at x squared. So therefore, the error is equal to the value of the first unused term. And again, it's going to be an absolute value, and I probably should have shown that right here. The error is going to be equal to this x value of 0.1, that's what x is, and whether I include this negative or not, the absolute value is going to make it positive. Now, just for giggles, I'll do this. The third power, but this is going to end up positive anyway. And we get that is how far off we're going to be. That is going to be the maximum error when x is 0.1. All right, so we have talked about Lagrange error. We have talked about alternating series error. Now let's do a little quick review, and then you can get to your assignment. Find m, find that maximum value. Get a little practice finding maximum values. If this is, the derivative that we have to use, that we find the maximum value of on this interval, where does this thing get as large as possible? 2 cosine of 3. What if I chose x being 0? That is within the interval. I guess I could have chosen negative 2 pi or 2 pi because they're the exact same place on the unit circle as the center of this thing, which is 0. I think that's where cosine is as big as it can possibly be. And 2 cosine of 0. Or if I had chosen 2 pi, 2 cosine 6 pi. Either way, maximum value I'm going to get is 2. What if I find this to be that first unused derivative? What's the maximum value on this interval? I think the maximum value is going to occur when x is 2. How about this? What if this is that first unused derivative? What x value in this interval can maximize that? 2 to the negative 3 is 1/8. I think 2 to the 0 probably. I think that's the biggest value of that first unused derivative. So that's just a little practice in finding those maximum values and what the thinking is behind that. Tell whether the function has derivatives of all orders. X over x plus 1. Well, let's see. Let's find the derivative. If I do a low, b high minus high, e low over low, low, I get that the derivative is, let's see, x minus x. I think I get 1 over x plus 1 being squared. And if I keep finding derivatives, will I be able to keep finding derivatives, or will I run into a dead end? And I think I can keep finding derivatives. I think I can find derivatives of all orders: first derivative, second derivative, third derivative. So whether we can? Yeah, and at x is 0 especially. At a is 0. I'm always going to have a 1 down in the denominator. So yeah, I'm going to be able to find a value of these derivatives. What about this guy? X squared minus 4. And this means absolute value. Well, I'm going to think about what that looks like. Because absolute values, I'm kind of suspicious of that they have corners to them. And I think this looks something like this, where this is what happens at 2. I graph that absolute value of x squared minus 4 on my calculator. That's what I'm going to get. And so, am I going to be able to find derivatives of all orders at 2? No. First derivative, I'm going to have a problem. So this one's a no, while this one was a yes. I'll be able to find derivatives of all orders here when x is 0. But here, I got issues when x is 2. And the final one we're going to do before we get going on our assignment, and the assignment is a lot of review stuff from the first couple of sections for the first 4 problems, and the final 4 problems deal a little bit more with the remainders. But question number 6. For approximately what value of x can you replace sine Wow, this just doesn't want to stay where I want it. I want to replace sine with just these first, remember 6 is 3 factorial, just these first 2 terms of the polynomial series for sine. What values of x can I use so that the magnitude of the error is smaller than this? 0.0, 0, 0, 5. All right. Well, sine is an alternating series. And therefore, the error is the first unused term. I use this term on, and I think of what sine is. Those are the ones that I've used. The first one that I have not used so that is going to be the error when I use this polynomial to approximate this function. So x to the 5th over 5, I got to keep that error under 0.000. Oops. Be the factorial there. 5. Well, if I multiply each side by 5 factorial, I think 5 factorial is 120. So I got to take this 0.0005 and multiply it by 120. That means x to the 5th. It's got to be less than 0.06. So now I got to use my calculator. I've got to do a math. Item 5, which lets me do the x root. I am going to take the fifth root of x to the fifth. I'm going to take the fifth root of 0.06. So when we do that, I get 0.570-ish. Or if I had truncated, 0.569. And so that is going to be the value of x. I can replace x with any value in between negative 0.570 as long as I use x's in this example, this approximation is going to stay at least this close to the sine of x. All right, assignment is in Schoology. You got 8 problems. Again, the first 4 are kind of review from previous sections. Final 4, dealing more with this error. And how far off are we if we use a certain number of terms of the polynomial to approximate the minimum function?